Hello, class 8. Today we are going to discuss about expansion of solids. There are different types of expansions in solids. Okay, so the first thing that we are going to discuss is linear expansion. Linear, as the word means linear, which is related with line. So here we are going to talk about a wire which has length, okay, but its breadth or thickness uh, is not that of not that much importance as its length is. Okay, so the length is considered more than its breadth or thickness. So let's say that there is a wire with the length L, capital L, and when this wire is heated up, there is a small increase in its length. Okay, let's say this much is the increase, and the increase is represented by small l. Okay, so here the change in the length is much greater than the change in its breadth or thickness. So that's why we consider the length to be more importance compared to the breadth or thickness of the wire. So we hear how much the length will increase when the heat is applied on the given length of wire depends totally on the material of the wire. If you take the same length of different wires and if you apply the same amount of heat, okay, or you increase the temperature in a similar way, for each degree rise in temperature there will be different length of increase for different material of the wire. So different increase in length for different materials are there will be different increase in length for different materials when the temperature increased remains same. All right, so this is actually because of the coefficient of linear expansion, which is represented by alpha, a Greek letter alpha. So what is coefficient of linear expansion is? It is actually the change in length compared to the original length with every degree rise in temperature. So this is the change in length, small l, and this is the actual or the original length with every degree rise in or change in temperature. Now this can be represented mathematically as change in length by original length times per degree change, means division is converted into its reciprocal multiplied with the reciprocal, that is 1 by change in temperature. So we can say that the coefficient of linear expansion is the fractional increase in length per degree change in temperature. So mathematically we can write this as alpha, the coefficient of linear expansion, is equal to the change in temperature, the change in length by the original length of the wire times 1 by change in temperature, that is 1 by the increased temperature minus the initial temperature. So T2 minus T1. Alright. Now since the two units for length and length, that will be meter, will be cancelled, and over here you will get the difference in temperature, that will be in terms of degree Celsius, which is in the denominator. So the coefficient of linear expansion will have the unit per degree Celsius. Alright. For example, the linear coefficient of linear expansion for copper is 1.7 into 10 to the power minus 5 per degree Celsius. Alright, and the coefficient of linear expansion in case of aluminium is 2.5 into 10 to the power minus 5 per degree Celsius. This means that per degree Celsius, okay, in every degree change in temperature, copper will increase by this much. okay, 1.7 into 10 to the power minus 5. And for the given length, in per for every degree change in temperature, or we can say the rise in temperature, there will be aluminium will be increasing by this much. So compared to aluminium and copper, which one will increase more is aluminium. So aluminium's length will increase more with every degree rise in temperature, and similarly with every degree fall in temperature, if the temperature goes down, aluminium will its length will decrease, okay, faster than the length of copper. Okay, so this is the linear coefficient of linear expansion, which determines how much the length is going to increase or decrease with every degree rise or fall in temperature. Next is superficial expansion. Superficial is actually the word or term which is related with surface. So over here, let's take a sheet of metal. Okay, over here the area of that sheet of metal is A, and when the heat is applied on this flat surface, okay, then there will be some increase, and let's say this much is the increase, okay, which is represented as small a. Then the change over here, the thickness of this of this particular body is not that much great compared to the change in its area. So change in its thickness will be very less compared to the change in its area. Thus the coefficient of superficial expansion, which is represented by capital beta, is actually the change in area, that is the increase in area, divided by the actual area or the original area with every degree rise in temperature. Alright, so we can write down beta, the coefficient of superficial expansion, is equal to change in area by original area times 1 by change in temperature. Okay, just similar to the linear expansion, we can also write this one in the similar way, only the difference is it was represented by alpha. Here we have beta, which represents the superficial expansion, and in terms of length, here we have area. Only that is the difference. So the coefficient of superficial expansion can be defined as the fractional change in area per degree change in temperature. So mathematically it can be represented as beta is equal to change in area by the original area times 1 by change in temperature, which is over here represented by small t. Alright, next is the volume expansion. Suppose let's take a three-dimensional object, a solid, okay, and it has some volume, okay, V, capital V, and when the heat is applied on this solid, on this object, it expands from all its dimensions, okay, and we get the change in direction as the bigger solid, okay, and let's say that change is small v, okay. So the coefficient of volume expansion in this case, since every dimension is changing, it's not the change only in length, neither only in breadth, neither only in thickness, every dimension is increasing or decreasing, it's changing. So the volume is changing, the volume is expanding. So the coefficient of volume expansion, which is represented by a Greek letter called gamma, this is gamma, all right, and this coefficient of volume expansion is actually the change in volume by the original volume times 1 by change in temperature. See, look at the first one, linear expansion. It was change in length by original length times 1 by change in temperature. Beta, the superficial expansion, was change in area by original area into 1 by change in temperature. Over here, volume expansion is change in volume by original volume times 1 by change in temperature. So this mathematically goes as gamma is equal to change in the volume small v by original volume capital V times 1 by the change in temperature small t. Okay, most of the time we can say that volume expansion is more relevant in liquids and gases than solids. Why so? Because solids, compared to solids, liquids and gases expand more according to their volume. So the gases and liquids are more relevant in terms of volume expansion compared to the solids. All right. Now we'll discuss about the relation between the three coefficient of expansions: the linear expansion, the superficial expansion, and the volume expansion. They are related. Okay, so they are related this way. Alpha, the linear expansion, is equal to beta by 2, that is the superficial expansion by 2, which is again equal to gamma by 3, that is the volume expansion, coefficient of volume expansion by 3. This is all because of linear expansion we are talking about is only one dimensional. It only deals with the length of the wire. Okay. Beta, that is the superficial expansion, is related with two dimensions, the length and the breadth. Okay. Area means length and breadth. So again it is divided by 2. Okay. And the volume expansion is related with three dimensions, the length, breadth, and the thickness. So over here it is again, in order to be equal with the linear expansion, it has to be divided by 3. So we can say that linear expansion is half of superficial expansion, and it is 3 times less than the volume expansion. All right, or if you multiply 3 with alpha, 3 times the linear expansion will be equal to the volume expansion, and so on. All right, so with this we come to an end of our video. Okay, in the next video we will discuss more about the thermal expansions. Thank you.